Okay, welcome to another 5 of the best 5 multiple choice questions from the AQA A-level Physics. Today I'm going to be talking a bit more about timing, because some of these questions, particularly this question, I found pretty challenging myself. Well, certainly to be absolutely sure of the right answer. Yeah, so we want to try and think about how we can get the timing good. So about 1 minute 30 seconds per question. As with always, please try to pause the video and attempt the question first. So first question, pause it and attempt it. Alright, so the question says we have 3 forces in the same plane, coplanar. Alright, so we've got 5 newtons, 4 newtons and 3 newtons. They all act on an object, and what is not the resultant? What couldn't be the resultant? So I think when you get a question like this, in order to be fast, the question's not hard, but in order to be fast, try thinking to yourself, what's the largest and what's the smallest force you could produce? So the largest force would simply be adding these all up. So that would be 5 newtons plus 4 newtons plus 3 newtons in a line. That's going to be the very largest force you can get. And if you add it 5 plus 4, blah, 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 that gets you 12 newtons in total. So the very largest force is 12 newtons, which is there. So we've got that. Okay, but then I just noticed there's a larger force, so that's impossible. So that makes D the correct answer. If you actually went through each one by one, you could see, I've got the answer now, so timing wise I'm happy. But just to be absolutely certain about the understanding, if you were to get, can you get 0? Right, is that a possibility? Is 0 a possible answer? Because maybe you're not sure. Well, if you had, let's say 5 newtons this way, 3 newtons this way, and 4 newtons this way, would that work? Well, you can check it out with Pythagoras, right? So Pythagoras would be a squared plus b squared equals c squared. So it would be 5 squared equals 3 squared plus 4 squared. 5 squared is 25. 3 squared is 9. 4 squared is 4 times 4 is 16. And they add up to 25 and 25, which means that this does work. So you can walk 5 meters this way, 3 meters this way, and 4 meters this way, and end up doing 0 meters. Yes, I know they're forces, but I think it's a bit easier to visualize when you think about them as displacements. So that one is possible. 4 newtons, is that possible? Well, that would be walking 5 meters this way, 3 meters, 4 meters this way, so 5 that way, 4 this way, which means we've been displaced by 1 meter so far. Then add on to that the final 3, gets you to 1 meter from here, plus the 3 gets you 4. So they're all possible, apart from this one. Okay, so let's have a look at the next question. This question would have definitely taken me more than 1 minute 30 seconds. Okay, pause the video, read the question. Alright, let's have a little look. Small sphere of mass m carrying a charge q. Now the problem is you guys, if you're in AS, won't have covered charge yet. So it's a bit unfair of me to put it in, but it's still worth a look at. Once you get your head around a little bit about charge, it's definitely worth a look at for understanding the vectors. Okay, so suspended from a thread placed in uniform, a horizontal electric field of a field strength E. When the sphere comes to rest, the thread makes an angle this. Okay, so the tension is that, and the weight is here. So we've got these 3 forces, right? You've got this force due to the electric field here. You've got the tension, and you've got the weight, and the thing is in equilibrium. It's reached, it's come to rest, so it's now balanced. So it says which one is incorrect. All right, so firstly, okay, just as a quick, if you're an A-level student, you're in your 2nd year, you will have covered this equation by now. So that is electric field strength is equal to the force per unit charge on an object. So the force would be the electric field strength times the charge. Okay, so that's very much like gravitational field strength equals force per unit mass. G equals the force per unit mass, and if you wanted the force, it would be mg. Okay, so force would be mg. Now, so that's what that is. So this F here could be thought of as also being EQ, And this W here could also be thought of as being mg. So that's step one. That's just going to help us access the question. So now we've got that bit out of the way, maybe you want to have another try at the question, because if you didn't have this access knowledge, this bit for instance, you might not be able to do it. But now you might be able to, so have another go. Okay, now if you've had another go, or you really stuck now, let's have a look at going through each one of these options one by one. So let's do A first. Well, the first thing I want to do is, this thing's in equilibrium, which means all these forces must add up to 0. Okay, now tension this way, weight mg this way, and EQ, which is the force because of the electrostatic charge pulling this way. So we've got T, mg and EQ, and this is the angle that we know. So it's telling us that this term here, T sine theta, is equal to EQ. Something is equal to this. Something using this angle, sorry, this magnitude and this angle can calculate that. Well, this is a triangle, right? This triangle is set up like this. That's the hypotenuse. The angle is here, which makes this the opposite. This is the adjacent, right? Okay, so if I'm using T and I'm trying to find EQ, if I'm using H and I'm trying to find O, I'm using sine. So sine theta will be equal to opposite over hypotenuse, which will be EQ over the hypotenuse, which is T. And then to get EQ as the subject, multiply both sides by T, so we get T sine theta equals EQ. So that makes this a correct equation. Okay. Now, this is actually one of the distractors, right? It's a correct equation, but they've done it in such a strange way. I'm going to leave it to last. So we're going to come back to this one, and that's exactly what I thought when I first had a try of this. I thought, oh, this is a bit weird. I couldn't get my head around it, so I left it till last. C, okay? T squared, that looks like Pythagoras. So let's just have a quick check. H is the longest one, so that would be like T squared. T squared should be equal to EQ squared plus mg squared. Right, that's basically saying C squared equals A squared plus B squared. Yeah. Now, these all should add up to 0, so this should be correct. So this one looks correct. Okay. D. Let's have a look at D. Okay, so what's D saying? mg equals EQ tan theta. Okay, so again, let's have a look at this. They're saying mg equals something. They're saying mg equals that, all those terms. So they're using mg and they're using EQ. Okay, they're using A and O. So that would be, whoops. Using A and O, that would be tan. So just remind myself, so car, toa. So it's A and O, I'm using tan. So tan theta should be equal to O over A. So that's EQ, which is the O, the bottom bit, over A, which is mg. Okay, so rearranging that for EQ, I get mg tan theta equals EQ. Okay, so that doesn't look like that. That's mg equals EQ tan theta. That's completely the reverse, right? So I could go back and check this again, but right now this looks like it is wrong. It's incorrect. But we're going to go back and look at this one. So by now I think I've answered the question, okay? Because I found one I definitely think is wrong. But I'm going to look at this one because I think it's really tricky of them to put it in here, and it is the distractor that the examiner's report said most people went for. So I'm just going to clear a bit of, no, I'll do it down here, this space. So what they've actually done here is they've imagined, okay, well, T's acting this way. Instead of trying to add them up in a triangle like that, they've thought, hold on, we've got mg acting this way, we've got EQ acting this way, we know there's an angle here of theta, okay, and they're saying to themselves, if I take each of these forces, this one mg, and split it up into two components, stop doing that, two components, here we can see this angle here and this angle here will be the same, so this is theta, okay? If I split this up into two components, I could resolve mg into this component and this component. I'm only going to need this component. But the component of mg that's acting in this direction and the component of EQ that is acting in this direction, when added together, should give me T. So I'm going to think about that now, okay? So let's look at that. So that's the hypotenuse, this is the opposite, and this is the adjacent. So for trying to work out the adjacent here, I can use A and H as cos, so it would be cos A over H, which will be cos theta equals A over H. H is mg, so it becomes mg cos theta, and that will give me the component of mg that is acting in the same, acting to counteract T. Okay. Now there's a component of EQ which I can add on to that, so I'll just work that out now, and that's why I've put the plus sign here, because I'm going to add it on. So let's have a look at EQ. Okay, well the angle here is not theta, it's theta minus 90, or 90 minus theta, sorry, I should do it the other way around, right? But let's do it on this side, right? That makes this angle theta, right? So, and I'm trying to work out this arrow here. So I know I've got the hypotenuse H, which is EQ, and I'm trying to find the opposite. So hypotenuse and opposite means use sine. So sine theta equals opposite over adjacent. So that's the opposite I'm trying to find over the adjacent, which is EQ. Rearrange for the opposite is EQ sine theta will equal the opposite. So add that on. Sorry, EQ sine theta will equal T. All added up equal T. And that is actually what you've got there. So that is gone from question mark to being correct now. All right, really quite a tough one, that, to be honest. Okay, so let's have a look at the next question. So for the next question, we just remind ourselves about these two conditions for equilibrium. The resultant force must be 0 if it doesn't have to be three forces, but the resultant force on the object in the x, y and z planes must all add up to 0, and that the principle of moments must apply, e.g. the sum of the clockwise moments must equal the sum of the anti-clockwise moments. Okay, so let's, having reminded ourselves of that, pause the video and read the question. Okay, so let's have a look at these then. The rectangular objects A, B, C, D are each 2 centimeters long and 1 centimeter high. Which one of the bodies is in equilibrium? Okay. Right. So there's those two conditions of equilibrium we have to consider. Okay. Condition number 1 is about the forces all balancing out, up and down. So we can quickly look at that. Well, A, does this meet condition number 1? Well, it's 10 newtons up and it's 6 and 4 down. So actually it meets condition 1. But does it meet condition number 2? Well, this is turning the thing in clockwise, this is turning the thing clockwise, and there's that counteracting it, but there's no way that it's going to exceed in terms, wherever we take moments from. If we took moments from here, 6 times whatever that distance is not going to counteract the 2 clockwise moments. So this one is not in equilibrium. Okay, this one potentially is in equilibrium. Now I can tell from the angles, this is because this is a 90-degree angle, that we've got 4 newtons this way, we've got 2 newtons that way, and we've got this 4 newtons this way. If I just shift this over to here, because it doesn't really matter as long as you're adding them tail to tip, right? So it looks like it could work. Okay, it's a Pythagoras setup as well, so 4.5 here, we've got 2 here, we've got 4 here. So if this meets the conditions of equilibrium, then they should all add up to 0, right? Because there should be no net force on the object. So that's C. So C squared plus B squared, sorry, C squared equals A squared plus B squared. Right, and I could crunch the numbers. 4.5 squared equals 4 squared plus 2 squared. Actually, when you calculate this, you get 20.25 equals 16 plus 4. So they don't appear to add up, but only by a little bit. I mean, it depends how we've rounded these numbers. Okay, so it's a possible for now. I'm going to leave it as a possible. In this one, we've got anti-clockwise, clockwise. So I'm not going to bother working it out, but what I can definitely see is there's a force acting in this direction, there's a force acting in this direction, there's a force acting in this direction. The force is never going to add up to 0 in the x, y, or z. So this can be discounted. Okay. This one here, similarly, these three forces are all have all got components that are acting directly upwards. So this has got a component acting upwards, so is this, so is this. So the three of them, between them, are never going to counteract in the opposite direction that force. So again, this can be discounted. So that just leaves us with this one, okay? And although it doesn't quite add up to in equilibrium, I think with the rounding, that's probably why. So I'm going to go for B. Okay, next question. So, pause the video, read the question. Now if we go through this one, it's pivoted, meter rule is supported in equilibrium. Of course it's in equilibrium, they're always in equilibrium. Horizontally by a thread inclined at 30 degrees to the vertical. Okay. Three forces acting on it, the weight. So let's say that the ruler is a uniform material, that means the weight will be acting here, W. Tension, which is going to be this way, T. And you're going to have a reaction force from the pivot. Now, straight away seeing this, if you've got this force, that force can be thought of as being made up of two parts, one straight up and one right. The weight and the upward force of that, the force from the pivot is going to have to be in this direction to counteract this bit, right? You're going to have a component acting in that direction. So now let's start thinking about which force would have to be the biggest. Now, sort of a shallowish angle, you've got the weight is producing a clockwise moment turning it this way, and the tension force is turning a anti-clockwise moment, right? The tension force, in a way, if you imagine it, if you had to hold this thing up, the further the weight of the ruler, the further away you are from the weight of the ruler in this setup, because the pivot is here, the less force you would need to pull up with, because to produce the same moment as the weight, you don't have to apply as much force because you're so much further away from the pivot point. So I think T is going to be smaller than W. Okay. I also think that F, the reaction force, R, is going to be smaller than W. W is going to be the biggest force. And the reason why I think that R will be smaller than W is R would be pretty much equal to W if W is directly above the pivot point here. So I'm going to start with a large W and then think about how I can use T and R. So I can see T would be in this direction and R could be in this direction. So it's going to look something like that. It's going to look something like W here, T is in this direction, so T here and R here. Now I've drawn it the opposite way around to the way they've done it, so I can flip it around. Order of addition doesn't matter in vectors. So if I wanted to draw it this way around with these arrows on this side, then I can do that, but I'd need to bring the R down to this bit and the T to here, so that'd be R and T. So actually these two things are equal, they're the same diagram, they're just in a slightly different order, just as 2 plus 4 equals 6, 4 plus 2 equals 6. It's just different ways of seeing the same thing. So W here, down, R is pushing up here, and T is this way. Which one does that match? It matches this one. Okay, right. Next question. Okay, so it's the final question. Pause the video and read it if you haven't already. Okay, so let's have a little look at what we've got here. We've got this lift. I'm going to draw the lift as a point mass of 500 kg. You've got a rope holding the thing up. You're obviously going to have gravity pulling the thing down, and gravity will be mg. So the force being pulled down on this object is going to be mg, which is going to be 500 times, well, we're using 10 in this, so it's going to be 5,000 newtons acting down. So just to keep this lift stationary and doing nothing, we must be providing already 5,000 newtons of force straight up. So the minimum force required is 5,000 in this case. So we can discount this, and this straight away. Now, if we want this object to accelerate upwards, we're going to have to continue providing the 5,000 newtons plus an additional force, which will be equal to the mass times the acceleration. So in this case, that mass is 500, the acceleration is 2, so it's an additional 1,000 newtons. So 1,000 plus the 5,000, 1,000 plus the 5,000 gives us 6,000. You could have taken a shortcut, you could have just said F equals ma, and the equivalent acceleration this time would have been the 10 plus the 2, which gives us the 12, right? And that would have got us straight to 6,000. Okay, I hope you found this video useful. Please comment, like, subscribe and share. Click the bell button as well. And if you have any comments, suggestions or queries, comment away and I'll try and get back to you. Thanks for watching.